Hello students and parents, welcome to yet another session from Concept Clarity, and this is Navitu here. So today we are going to talk about graphs. We have talked so far about speed, we have seen velocity, we have seen how velocity is related to displacement, we have seen how speed is related to uh, the change in distance versus time, and then we have seen about acceleration. Today we are going to see how a position and time of a particle can be represented on a graph. The graph which represents the position and time is also called as a xt graph. Okay, by meaning position, it means displacement. So let us get on to our discussion. I'll clear this. So let us draw a graph first. We'll take a sample graph. This is a sample graph. This shows the position and this shows the time in seconds. Okay, this is called as the xt graph. It's also called as a position time graph, because it represents the position of the object at any given time. So at any given time, we can find where the position of the particular object or the particle is. Right. For example, if I want to find out the position of the object at this particular time, then I can draw a line parallel to the x-axis, and I will know what will be the position of the particle at this particular time. If this time is t1, then this position can be called as x1. Okay. So we know that average velocity average velocity is the change in the position divided by change in time. So this xt graph can give us the average velocity of the particle for any given two positions. So now if I draw a line connecting the two ends of displacement, if I draw this line, then this will be called as theta. Then I can say that tan theta is equal to, if I draw perpendicular, this line represents delta x. Am I right? This line represents delta x because this is the change in position. If I call this as the initial position xi, and this is the final position, this is t initial and this is t final. At some particular point of time, this will be t final. So I can get change in displacement from the slope of the graph itself. The slope of the graph, which is represented by tan theta, will give me the average velocity. So here we get to know that slope of any line in this particular graph, slope of any line on this particular graph will give me the average velocity. If I draw another line which connects two points, which connects these 2 points, then this slope theta dash will give me the slope. That means it will give me the average velocity of this particular particle between these 2 points. If I call these 2 points, let me call these 2 points x2 and x3, and this time interval I will denote it as t2, and this time interval will be t3. So the slope theta dash will become equal to x3 minus x2 divided by t3 minus t2. This is going to be the slope of the graph, which is also equivalent to average velocity. As you can see, if you can either theta or theta dash represents the slope of the graph at any two given positions, and those two positions represent those two particular time periods. So what is instantaneous velocity then? Can we find instantaneous velocity from this particular graph? Yes, of course we can. Let me take it on the new slate. I'll clear this. Let me draw the graph again. This was the graph which we have seen, right? This is the x meter and this is time in seconds. So now we're talking about instantaneous velocity. We know that instantaneous velocity can be given if we shrink the time period, right? That means delta t is tending to 0. So this means that the first derivative of displacement with respect to time will give me instantaneous velocity. So now if I have the time period from here to here, which gives me the average velocity, I will shrink the time period. I will bring it as close as possible, such that I have a very small time period. I have a very small time period. And this very small time period is called as dt. Okay, and for this small time period dt, this will be the small change in displacement dx, right? From here, I will able to find the instantaneous velocity. So we know that the line joining any 2 points on the graph from here to here will give me the average velocity. Now, if I want, at that particular instance of, if I want to know the velocity at that particular instant, then I'll have to draw my line as close as possible to this particular point. And if I draw my line as close as this particular point, then it will appear as a tangent to the graph. This will be the tangent. So I know if I take a slope now here, theta, if I take the slope of the graph here, or if I take the slope of any tangent anywhere else, theta 2, this is theta 1, then I will, then from this particular theta 1 or theta 2, I will able to get the instantaneous velocity at that particular point, at this particular point, right? Here, in this case here. So if I draw a tangent on the graph, if I draw a tangent on the graph, I will able to get the instantaneous velocity at that particular point. So we also know that if the first derivative of the function, that means the first derivative of the graph is going to give me the instantaneous velocity. If the graph is represented by function fx, then derivative of fx with respect to time is going to give me the instantaneous velocity. The first derivative is going to give me the instantaneous velocity. So let us deep dive into the graph. So I'll clear this out. We'll deep dive further into the graph. Draw the graph again. We know that this is a horizontal line. Even here, this is a horizontal. If I draw a line here, the tangent to the graph will appear horizontal. This is also horizontal. So now we know if the line is horizontal, that means parallel to this axis. This is an xt graph. It's an xt graph. So slope of this line, slope of the horizontal line is 0. That means that dx by dt at this particular point of time at horizontal is 0. Here also dx by dt is 0. That means velocity here is equal to 0. Velocity here is equal to 0 when it is parallel. The tangents are parallel to the x-axis. That is when velocity will be 0. So now this particular instant from here to here, it appears that it will be a straight line. It appears like a straight line. So the tangent drawn from here to here at all these points, at all these points, from here, 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 at any point on this particular line, it appears that V is same, right? V appears same because if I draw, if I find a slope, if I find a slope, this line is a straight line. So it will represent multiple right angle triangles, multiple similar right angle triangles, right? If I draw a line here or here, it is the same angle which it makes. So that's why I can conclude that V is same. V is same means V is constant. So if the line is straight on the graph, if the line, the tangent line can be drawn straight on the graph, that time V is a constant. That means V is same. At the curved region, here this is the curved region. At this curved region, V is changing. This is straight line. Straight line. But making an angle theta. I'll say theta dash. Okay. This is theta dash. Now here at this curve, it is obvious that velocity is changing. From the graph, it appears that velocity was initially 0 and now it is increasing. What is happening to velocity? Velocity is increasing. And here we notice that velocity after increasing, it is now decreasing. Velocity is decreasing as per the graph, right? If you draw a tangent here, if you draw a tangent here, then if you draw a tangent here, and if you draw a tangent here, we can see that the angle is actually increasing. This angle here is more than the angle before. That means velocity is increasing. That means slope of the graph is increasing. Now the slope of the graph became constant at a particular point of time, and as it was increasing, it now started to decrease. So now if I draw the lines here, if I draw a line like this, tangent, then another tangent here, and another tangent here, you can see that this angle is bigger than this angle and is bigger than this angle, right? So this, the angle here is more than the angle here and angle here. This is at the higher point. The angle here is smaller, the angle here is larger. So we can say that the slope of the graph is continuing to decrease. That's why velocity is decreasing. So we have understood in this particular session how to read the xt time graph and how to get the average velocity and the instantaneous velocity. So let us summarize quickly. I will summarize on the graph itself. We had a graph like this. Then we know that average velocity when be given as, if I can take 2 points on the time and if I can take 2 points on the x, I want to average velocity between two instances of time, right? So I take these 2 points, I take another point at this time t2, at this time t1. I plot on the x-axis. This will be x1 and this will be x2. So I'm measuring the average velocity between t1 and t2. So average velocity will be x2, which is final, minus x1. So this x1 will take the negative sign. It will take the negative sign. You can put negative associated with x1 because it is below the graph, divided by t2 minus t1. This is going to be my average velocity. Now if I want to take the instantaneous velocity, then what do? I shrink the time period. I bring the time period as close as possible to that particular instant of time, which is now called as t3. So now at t3, I will draw a tangent. I will draw a tangent. Now let me draw a tangent. Okay. At t3, I draw a tangent. I hope you can imagine this tangent. I hope you can imagine this tangent. Okay. This is the graph and this is the tangent. So then I can say the slope of this graph, theta, is going to give me the slope of this tangent. The slope of this tangent, which is going to represent a shrunken time period, is going to give me the instantaneous velocity, right? So going to give me, and the derivative of displacement with respect to time is what is going to be the instantaneous velocity. So average can also be found with tan theta. We call this tan theta as the line joining this point and this point. So it will be this line. It is not a tangent, it is just a line joining the 2 points. So this will be theta 1, theta dash. Theta dash is equal to the same delta x divided by delta t. Delta x is x2 minus of x1 divided by t2 minus t1. And then instantaneous velocity, which is tan theta, this I'll call theta, which is the tangent here, which has no 2 points. It is that at that particular instant, it might be very small. It might still have the 2 points, but it will be very close to each other. So tan theta here, if I want to find the slope of this tangent, which is just touching, this is the tangent touching the slope, touching the curve, then tan theta is equal to dx by dt. Then we also saw that if dx by dt slope is 0, then velocity will be 0. Now as the angle as dx by dt or tan theta is increasing, it implies that velocity is increasing. If dx by dt, as you go along the curve, as you go along the curve, if tan theta decreases, then velocity also decreases. So these are all the observations of the graph. I hope you have found this helpful to read the graph. Okay, so please like, share and subscribe if you have enjoyed this video. Thank you.